Good morning or good afternoon, everyone, whoever is looking to this presentation. This is the main talk about quantms, proteomics using Nextflow. And the idea of this presentation, and also a little bit, I will be doing a little bit of demonstration with local computers, but also HPC clusters. Um, I would like to say that I'm sorry that the final cloud infrastructure didn't work for me because I have some issues moving data from local infrastructure to the AWS. But in the HPC works similar to the cloud infrastructure, then I think is worth it to the presentation. Today I will be talking about quantms. What is quantms and what allow you to do? First, I will discuss present a little bit about PRIDE, what PRIDE is, SDRF. There is a full presentation associated with this talk around SDRF, the sample metadata relationship file format, and then I will go into details about quantms. What is quantms? Why is cloud-based, and what allow you to do? Protein Exchange Consortium is actually a consortium that groups a lot of databases, including Massive, PRIDE, iProx, and JPOS. The main database of Protein Exchange is PRIDE. I am the team coordinator of PRIDE. It's stored in this database is hosted by NBL and is the major archive. It hosted more than 80% of the data of Protein Exchange. Currently, more than 30,000 data sets are public data sets are out there, which actually triggered a really long, a really difficult problem for proteomics. I mean, we want to be able to reanalyze massively and fast most of the public data, but also in distributed environment, not in a single machine. And that's what this talk is all about. The number of data set is actually growing so fast. For example, by 2021, we have submitted more or less almost 500 data set per month, which basically is a lot of data that gets deposited every month and should be available for reanalysis and repurpose. There is a full presentation of the about SDRF associated with this talk, and we will leave the link somewhere. But what is the SDRF? In proteomics, when you deposit the data, you put only right now until 2021, you put only the data files, the raw file coming from the instrument, okay, and some metadata associated with it. Title of the experiment, data protocol, sample protocol, and a short description. Who are the authors and so on. Mainly also result files, like for example, the files coming from the search engine or the quantitation tool like MaxQuant, and that's it. In 2021, we released a file format that tried to describe how the samples, okay, the samples analyzed in the experiments are related with the raw file. And this actually is the SDRF, is sample to data relationship format. For every sample, you need to describe in which file is and actually the metadata around the sample. All the quantms is based on SDRF. It takes as an input SDRF to perform the analysis. Okay, as I said, because this is so important, I made another presentation associated with this one. Let's talk about analysis. I mean, we know there is a lot of data out there. Now we have with SDRF a way to describe the data. There is multiple tools in proteomics. I mean, tools go, you can see here the most popular tool for quantitation continue to be MaxQuant, but there is others. There is OpenMS, Pattern Lab, Skyline also is really popular. And these are free for academics mainly, but there is others, open source, some of them also. And there is the commercial ones. The commercial one, Protein Discover is really popular. Scaffold, this is actually a survey I did in 2019, more or less, about the popularity of open source and commercial software. You can see here how mascot was for a long time the best the most popular tool until the 2010, more or less, for analyzing proteomics, and it was taken over by MaxQuant. But recently, there has been a split. I mean, there is other tools that have been becoming more and more popular, like FragPy and MSFragger. You can see here in the number of citations how, for example, MSFragger has gained quite a lot of attention recently. This is from 2012, sorry, 20. And other search engine tools and so on has lost a little bit of attention. And how, for example, MaxQuant doesn't gain anything, but it doesn't lose anything. I mean, it meant to be the main tool for data analysis within the open source and freelance community. In open source, but free options for proteomics analysis. But I want to say something really important. The best tool is the one that works for you. I mean, the one that you are familiar with and so on. Most of these tools, and that's the purpose of this talk and also this course in general, are desktop oriented. Mainly, everyone uses these tools as a monolithic tool that they have in their computer. They put their data and they analyze their data. There is some cases, I think FragPy, you can run it from the command line, extend also, but they are not oriented to distributed OpenMS, of course, but they're not oriented to distributed environments, okay? The main focus of the tool is not to be run in a distributed environment, in the cloud, in HPC, and so on and so forth. Their main focus is to be computed in the mainframe with a lot of memory, a lot of CPU, when you can run as a whole the entire experiment, okay? That's why we created quantms. quantms is an alternative to go to cloud and perform your experiment, but also to go to HPC, high performance computing, to basically gain some of the ideas of or take advantage of some of the possibilities of the cloud environments and then reuse that for proteomics analysis. In 2021, I think, 22, actually, we published a review, which is actually here in Proteomics 2020, actually, where actually we described what was the main, what can be a workflow in proteomics that should be basically moved. How do you move a workflow in proteomics into cloud infrastructure? And the first step is that in a proteomics, in general, in a computational proteomics analysis, you have multiple steps. For example, if it's labor-free, you have feature set detection, you have the database creation when you actually create the decoy database, you have the database search when you actually take the spectral data and try to associate to a peptide, each spectrum. Then you apply some FDR and statistical criteria to discard peptides that are low scoring and keep the ones that are high scoring. In some cases, you do a second database search to actually do a more accurate search of the space, and then apply an FDR. Then you do protein inference and quantitation of the data. Okay. Then this can be divided into small steps. In all of these monolithic tools, what they do, Quant and other tools, they group all these tools into one piece of software and perform all the steps together until the downstream analysis. What actually we propose in 2020 is we should look for a more distributed approach. A distributed approach will look like this, where actually each of the steps that you want to perform is actually an individual tool that is associated with a Bioconda Docker container. And I will explain about those concepts, what those concepts are. What is a Bioconda package? What is a biocontainer? That will allow you at the very end to take each step and perform each step in one specific node of compute. Okay? Then you perform feature detection in one compute node for one raw file, and another feature detection for the other raw file in another compute, and so on and so forth. Every search in another compute, then you get some result. Then you perform identification in the same way, FDR filter, and probably because protein inference is the step when you group all together and perform FDR and group all the peptide for every row, every sample into a big node. But all these steps can be done independently in different nodes. And more importantly, it should be relevant for the user. Where do you perform that? What that means is basically you don't need a computer, you don't need an installation for your personal computer, and another installation for example, AWS or the cloud infrastructure, and another installation for the HPC, and so on and so forth. Everything should be deployable and reusable as easy as possible with the same setup. And that's what was our vision, and that's what we try to pursue with quantms. Quantms is quantitative analysis of mass spectrometry oriented to cloud reanalysis of proteomics data. It's based on the popular engine or workflow engine called Nextflow, and I will talk a little bit about that. And it's DSL2, and it can perform. There's multiple features, but one of the main features, it can perform 3 types of analysis: LFQ, DDA, label-free data-dependent acquisition analysis, TMT analysis, and DIA analysis. The 3 of them can be performed with quantms. In the future, we plan to export this to SciLab, ACTRA, and other labeling methods, but for now, these are the 3 main focus because we know these are the main data sets that are out there in the public domain. The second thing is, for quantms, it's extremely important to be reproducible and to be based on a standard file format. What that means is that the file formats underlying quantms, all of them are standard file format. And this is actually really important because a standard file format like MCTAT, MCML, and so on and so forth has been developed by a huge community. Everyone can build their own tool to read from quantms or to process the results of quantms, and you don't really need proprietary software to understand what has been the output of each file, okay? The input is an SDRF file format, as I explained before. This is how do you describe the sample. The raw file is an MCML. Of course, we have some notes that in the quantms that if you have raw file, converted to MCML, and the final output is in MCTAT. Mainly in the core of quantms, there is OpenMS tools and also Diane to perform the analysis of data-independent acquisition data. Okay, how this look like? I mean, this is a small diagram of what will happen when you have an experiment with quantms. And this is, I hope you can follow me with this small diagram. You have the MCML data or raw file, and you have a FASTA file. It's optional that you can generate the decoy. You can provide your own decoy, or you can provide, or if you don't provide your decoys, the pilot will compute the decoys, will calculate the decoy for you. It is also important that another input is the SDRF. The SDRF explains actually the experimental design, is how actually how quantms can know what is the raw file to where to send the raw file and split all the experimental design into multiple nodes of compute. Okay, then if you continue following, there is a small step here to index the MCML because it's needed for some statistics and so on. And then the user can opt to use 2 search engines, MSGF+, which is an open source software, and Comet, which is another open source software. Then you can use both of them, and you will need to combine the results of them, or you can opt, optional, you can use only one of them. This is actually depending of the cloud infrastructure you're using, actually. Because, for example, we know, and I will put some statistics, that Comet is actually is quite fast, but consume a little bit of more memory than MSGF+, but of CPU than MSGF+, while MSGF+ is quite slow, but actually in some cases can give you more PSM. It depends on the study. I would say for a normal data set, you can go with Comet. It would be really fast, and you will not need to consume that much CPU memory in your analysis, and you will have decent results in terms of PSM and peptides. However, if you are going for a deep analysis, then you may need to combine both search engines and consume a little bit of more memory. You have the consensus ID, which basically combines the two steps. Then you have percolator on top of it, which basically percolator will try to boost the number of identifications for the results. I mean, What Percolator does is have put on top of this some support machine learning method that take the original identification and try to, using a different property, try to boost the number of identification. I will not go into detail there, but you can read about Percolator, how it does that, and so on. Then we use, if you are doing PTM's localization, PTM localization studies, then you can use Lucifer to actually try to localize the PTMs in a better way. Then at the very end, okay, then in here, every step is independent. And if you see, every raw file actually can go through all of these steps independently. However, at the very end, we have what we call like a heavy node. And this node, what it does is actually to perform protein inference, because in the protein inference, you need to actually say the FDR for the entire process. And that is actually a heavy node. It uses more memory than all the other steps. And actually, one of the really cool things with cloud or quantms approach is that you can define, and I will explain how it does that, you can define how much memory you want to, in average, you want to allocate for these small steps, because this is for independent raw files. You can start by allocating, for example, 10 gigabytes of memory, really small node, and then you can go hide, and then have a really big node with, you can start by 70 gigabytes, 100 gigabytes, dependently of the size of your experiment, for the big processor at the very end step. But you don't need a big node allocated for months for the very beginning. You just need small steps, okay, very well configurable for a small amount of memory, and then a big step that will perform only one task, which is the protein inference and final quantitation table. At the very end, we also support to MCTab, but also other file formats. And if anyone here listening to this talk is interested to collaborate with us, just ping to us, and we can actually try to export to different file formats. I mean, we have now MStats, but we can do tree-clear and so on and so forth. This is for DDA experiment. I mean, I explained the LFQ label-free thread, but this is the same thing if you go for TNT. There is an isobaric analyzer that try to get the isobaric level of every peptide, and then you have the protein inference and the protein quantifier, which are the big nodes. I mean, all these small nodes are the same here, okay? And in DDA, MSDF, this is shared between LFQ and TMT, and the only thing that is different is how they quantify. More interesting, I mean, we can perform DIA analysis using Diane, and that's the completely different thread, because we are for now supporting only DIA library-free approach, where actually you start by the raw file, where we can actually convert for MCML only for thermal raw file, but if you are using your AVSAX or other instrument, you need to convert to MCML yourself. And you don't need to add the decoys. I mean, this decoy step is not shared here. Diane will do that for you. Then in Diane, we use every raw file is sent to a node, where Diane will try to predict the in silico library from every node. No, it will generate the in silico library for the database, and then we do a pre-analysis of every raw file, and then we'll combine this each analysis in the latest step, and then finally have an MCTab, generate an MCTab and MStats. I explained this this is the general behavior of the workflow, but these are the small steps, how this is happening here. And what is, actually, I want to do a stop here about the file format. File format in quantms are based on, as I say, standard file format. All the output, all the input are PSI file format. PSI is the HUPO standard proteomics standard initiative, and they actually is a group of developers, bioinformaticians, biologists, and so on, that they group all together and define a set of standards in proteomics. The input is actually an SDRF, as I explained before, and the output is an MCTab. And this is really important because the MCTab is what contains your results. An MCTab is a tab delimited file format also. It has a first section that contains the metadata of the experiment, a protein section when actually all the reported proteins are written, and then where, for example, in that you have the protein accession, protein description, best search engine score, and the quantitative values, intensities for every protein across the entire experiment, for every specific sample. You have then a peptide section when you have all the peptides associated with these proteins, and the final, the PSM sections, when you have all the PSM spectrum associated, peptide spectrum matches, where actually for every peptide you have the association between the spectrum and the peptide. We also have popular other output format like MStrats and Tricler. Okay, let's go now to how you can run this, and that's when things get interesting. Okay, then as I said, and I have a really nice presentation about SDRF, how an SDRF look like. But in the SDRF, you put the configurations of the search. For example, the proteomics search. Let's say you have the PTMs that would be used for the searching. You have the enzyme that was used for the cleavage, like in this case, trypsin, for example, and I put some examples around that. You have you can have also other parameters, more generic parameters, and so on and so forth. Then, how do you run Nextflow? You need to first install Nextflow, and I will not try to go that big into Nextflow because there is a lot of information in internet in Nextflow. But in a simple computer or in HPC, you can do something like this and install your Nextflow. Nextflow is the workflow engine that will understand your quantms. It will be the one that actually know what kind of engine I'm using for deploying the tool, if it's Docker, Singularity, or Conda. It will be the one that knows what type of computer I am trying to deploy, or architecture I'm trying to deploy, if in this case it's an HPC, a cloud infrastructure, or my local computer. That is done by Nextflow. You can go in internet and look for Nextflow information and so on. How do you run? I will put a really simple example. How do you run quantms? You first download quantms to your local machine using GitHub clone, and then you download your Nextflow version, your quantms workflow, and then you type a command like this. As I said before, this is not a desktop tool. This is not something to run in with a desktop environment. There is some options to run it in desktop environments and so on, but mainly this is for the command line. This is how do you perform an analysis in cloud infrastructure, in HPC, in your command line with large studies. Then you run something. Nextflow is basically that you're running the Nextflow workflow that you run. Main is the main file of the workflow. A configuration file, I will go in details about how it looks like. A profile, and that's, for example, this is EVI cluster. This I will explain this. This is a profile, how it look like. The root folder is where this will be exported, where the raw data is contained. The input is basically an SDRF, the database that will be used for the data search. Add or not decoys. In this case, I'm adding the decoys. The search engine that I want to use, MSGF Plus or Comet. A threshold at the PSM level, 1% FDR, or 1% FDR at protein level, and then you run the experiment. Actually, from here, you can remove the add decoys if your database has the decoys, and you can even remove the search engine parameters, because there is one search engine parameter which by default, which is Comet, and you can also not provide the PSM threshold or protein threshold, because both of them are put at 1% FDR, which is actually the standard. I just put here how the command look like. Okay, in this case, let's go in more detail about the command. Here I'm saying I am performing this analysis with EVI cluster profile. In our Nextflow workflow, EVI cluster profile look like this, and profiles are basically what type of architecture, compute architecture I will be using. I will be using an architecture that will be using for the container deployment conda, that Docker will not be enabled, will be false, Singularity will be false, and I will be trying to use Mamba to deploy the conda package. If I'm using Docker, and mainly, for example, in this case, this is actually my way of executing in my local machine, I will be true for Docker, and all the other one will be false, okay? What will happen? Will happen something like this. This is how steps will, this is the granularity of the step. That's how things will be thrown into the cluster, into the different steps, and each step would perform one task, okay? And interesting enough, and I will try to point it out here, for example, in this test, this is a library generation from a FASTA file for DI experiment analysis. In this step, the first attempt to perform the experiment, to perform that task, failed. And it can fail because of memory, for example. In this case, it's because of memory, because I give to this task, I don't know, 10 gigabytes. I want really this to happen in a small machine. However, for this FASTA file, it cannot happen. It goes out of memory. Nextflow provides a way of retrieve the same task again. Then what is happening here, automatically will try to allocate another node with more memory, which, for example, you can define the threshold. In this case, is twice of memory that it was in the previous step. Then it is trying to run now, and it passed actually in a second node with 20 gigabytes of memory. This is done automatically. And this is really cool because you can go, for small steps, you can go from really low memory, incrementally going to have as much tries as you want, depending on the size of the experiment. Then at the very end, and that's what something I was explaining before, you actually have a report, and I will put some examples, real examples about this, about the memory size, how much it takes to run each step. For example, this is MSGF. It takes, for example, quite a lot of RAM to run, but in terms of CPU, for example, I think CPU is smaller than Comet. Comet has a little bit of more CPU, but in terms of RAM is low. With those variables and with a lot of experimentation, you can see really how in your cloud infrastructure you can use one or the other search engine or both of them. Then I will, as part of quantms, we release also the QC reports of p-multi-QC, which is a library. At the very end step, we have a library that releases some really nice reports around the experiment, what has happened during the experiment, and I will go through examples. I will not go into detail. I will explain this with a real example. Finally, this is really important. When you finalize your experiment, quantms in the output folder will actually release a set of folders that contain different output for the analysis. For example, the search engine for Comet results, the MStats converter results, and so on and so forth. Including for MStats, for example, we have all the output of MStats, including plots of the volcano plots of differential express proteins, and so on and so forth. We have used this pipeline with multiple data sets. Recently, this year, we published a reanalysis of multiple cell lines to try to find out ensemble variants, ensemble-based proteomic non-canonical peptides, and this is actually a collaboration with Leitos Group and Rui Branca. You can go and read about how this quantms was used, and now we managed to reanalyze 6 data sets in Prime, more than 65 cancer cell line, 20 million SMS, and we find out around 2,000 mutant peptides that were really relevant, and they are understood. Thanks to the guys of OpenMS first, Timo and Giuliano, who are the main supporters of the tools, then to Vadim for Diane, and our team with this collaboration with Professor Chen Minsei Bai in the Chong Key Laboratory. But let's go over some examples. Let's go over first about how p-multi-QC look like. When you finish, P multi-QC actually is the report of your final experiment. This is how it looks. This is a real example of P multi-QC. This is the analysis of protein exchange dataset PXD 004684. And the SDRF, I think, is the one that I showed before, or if not, I can try to look for. Then at the very beginning, you have all the MCML files that were used and the sample metadata, label, MSTAT condition, replicates, and so on. Then you have the number of, this is a DI experiment. Then you can here have the number of peptides identification, modified peptides, the number of proteins, and as you can see, you can see here for every run, for example, these two specific runs, you have really less peptides ID than the other ones. This is actually really important for you when you finish the experiment. If you want to remove some of the raw files and perform again the experiment, this is actually really helpful to like a QC to basically see the accuracy or how the experiment performed. We have the number of peptides per protein. We have the number of MSMF, the peaks distribution, and actually really nice, you can actually see here the number of all the peptides identified, and you can actually search by peptide. More interesting, you can see, for example, the average, the best search engine score for every peptide, and you can see actually the average intensity across all the replicates. You can switch here with show replicate, hide replicates. You can see here for every condition under study, for each sample, the intensity of the peptide on each sample, okay, for each specific replicate. You can see here for every peptide, and this is something you can also see for your proteins. You can go see here, okay, these are my protein of interest. I want to see this protein, and this, for example, for this particular protein, average intensity is this one. It has number 5 peptides identified, and these are the intensity for this particular data set, for this particular condition, and the intensity for this particular condition. This is really beautiful because you can see as a DI experiment, when you have a really nice reproducibility, you can see here that the intensity is more or less the same. All the replicates, you don't have so many missing values, but we can go to another experiment. We can go to, this is actually, this report is in the summary pipeline. We can go, let me see if I can find pipeline info. This was a data set that I run before in our cloud infrastructure. As I said, sorry that I didn't have the cloud infrastructure running for the training. I have some problems moving the data. Okay, this is the report about my data set. How much things consume. For example, we have the in silico generation. It doesn't consume that much CPU. In terms of memory, actually, the preliminary search actually consume quite a lot of memory, and the in silico library generation consume a little bit of memory, but you know, more or less in general, 6 GB, 2 GB of memory consumed, and so it's not that really that much. But job duration, for example, in silico generation, for example, library is the one that consume more time. You know, you need to give more time to it, and these are the times where every task was performed. Then I will go back to here, and then in the MStats, you can see, for example, when you have the MStats report, and you can go and see and open this volcano plot, this lovely, beautiful volcano plot, when you can see all the proteins that were identified, okay? And differential express for this particular data set. Okay, let me try to find out, because I have multiple data sets reanalyze it, and let me try to find out a TMT. Okay, this is a TMT data set, and let's go to summary of the pipeline. And to show you something, because this is actually quite relevant in the multi-QC report, this will take a little bit of time. Okay, then here you have more conditions. You can open here and see a little bit more condition. But there is a really nice heat map when actually for every sample you can see kind of the differences between samples, MCML, sorry, raw files, and different variables. In this case, is contaminants. For example, the difference between contaminants here and contaminants here is quite a lot. And then you can here spot what are the samples that actually may be, or your runs that actually may be been going wrong during your experiment. And this is quite nice because here you have the number of peptides identified in the pipeline, number of peptides, proteins identified for every run, number of peptides and proteins. But here you can go more in detail. In this case, we use MSDF Plus and Comet. And if you see here, MSDF Plus identify generally a little bit more proteins that a peptide PSM than Comet. But it doesn't improve that much, I would say, the number of final peptides. But you can see here, for example, for these fractions, okay, for these fractions, actually the number of PSM is really low compared with this fraction. This kind of report is actually quite useful for users. We have other reports that are quite nice, like, for example, correlation of scores. I mean, you can see the score correlation for decoys and targets, how targets and decoys are split across the sample. And you can see the same thing for the MSDF Plus spectrum values, okay, which is quite nice. And again, you can switch. Let me see if I can see here, for example, for peptides, you see here the same thing, amount replicates for these peptides across the three conditions. Remember that norm, no, not remember, I mean, in the other talk I was talking about what norms means. For MS stats is actually the pooling of the MS stats, okay? Cool. Let's go to the command line and try to find, for example, like here running one data set is the DI data set. This is how, this is the example that I put. For example, this is in my local computer. You can run, you can download quantms from GitHub, and from I'm using now the development version of quantms. And you can run it with this simple command, Nextflow main, and then you can use Nextflow config, and the Nextflow config will define some sort of parameters. I'm using Docker, and this is the text, test data for TNT, and the output directory would be in this place. If I say resume, it will start from the previous run that was performed. And this is actually, Nextflow will go into, this is running locally in my machine, and I have another one running locally in the HPC. In the HPC, you will see that every step is running. Here I'm running at the same time, I'm running 127 jobs, 70% of them has finished, and in total, they need to run 145 nodes. But this just one node for them and MCML statistics. Here, this is how this starts, and then MS will start triggering this approach because these steps were successfully before. When I say resume, Nextflow will understand that this has finished successfully, and then I can move to the next step, because in this case everything has been successfully so far. I just want to trigger the pipeline in my local machine using the command. Then it's trying to basically collect, this always happens, it's trying to collect the statistics about the run. I mean, the run, everything happened, and it's trying to collect the final statistic. Okay, I think this is we can stop the presentation here. I hope for the interactions, if you have questions, we can actually discuss it more in detail about quantms. Please, you can talk to us in GitHub. The GitHub of quantms is actually sorry. Big Bio, quantms, and this is the development channels. I mean, this is the latest version of quantms, the one that we have on the active support. And here in the discussions, you can type your own questions and interact with the developer team. Thank you for everything and for your attention.